Alright, let's look at the homework 11.1, problem number 10. Alright, so what we want to do is we have a sequence defined by this recursive formula, and we want to show that this AN is increasing and also bounded above by 3. Alright, so let's do that. Alright, so first thing is I'm going to try to show number 1, the sequence is increasing. Right, so what we want to do is we want to show, we want to prove that for all natural number n, we have to show that an is less than an plus 1. Right, so let's use the induction. So it's a proof by induction. Alright, so let's do the base case. Number 1, base case. Alright, so when n equals 1. Alright, so we just have to check here. We know that A1 is defined to be 1. Right? Then A2 is just following the formula. It's going to be 3 minus 1 over A1, which is 1. So this is equal to 2. Right? So 2 is definitely larger than 1. So this tells you that right, A1 is definitely smaller than A2. Right? So base case is verified, right? And the next step is number 2. And we need to show that, actually we need to just assume that this is an induction hypothesis. When n equals k, then we have this inequality. So we assume that AK is less than AK plus 1. Alright, so here's the assumption. Right, then another thing we can assume that since A1 is 1, then we're trying to show that it's increasing. This guy is, we can assume that the AK is greater than or equal to 1. Alright. Then number 3, so this is the last step. We want this is called the induction step. Right, so we have to show that when n equals k plus 1, we still have the same inequality. So we need to show that a k plus 1 is less than a k plus 2. Alright, so what we can do is you can start from what we know. So by induction hypothesis, we know that the AK is less than AK plus 1. Right. The next step is I'm going to just take the reciprocal of both sides. Right, so you have 1 over AK and 1 over AK plus 1. Alright, so these are positive numbers, and if you take the reciprocal, the order changes, so you have to flip the direction of the inequality. Alright, then I'm gonna go actually up here. Alright, then I'm gonna multiply by -1 to get the negative 1 over AK and the negative 1 over AK plus 1. Alright, again, we multiply by negative number, so we have to change the direction of the inequality once again. Alright, then we're going to add 3 to both sides. We get the 3 minus 1 over AK is less than 3 minus 1 over AK plus 1. Alright, this is by definition. Left hand side is exactly the definition of AK plus 1. And right hand side is the definition of AK plus 2. Right? Which is the inequality we're trying to get. So we have that. So we say therefore, hence, we have for all n natural number, an is always less than an plus 1. Right? So this will show that this sequence is increasing. Right? Now we need to show number 2. We need to prove that this an, so for all n natural number, right, an is bounded above by 3. Right? So let's apply the induction here. Proof by induction. All right. So first step is base case. All right. So base case is when n equals 1. All right. So we just have to check. We know that the a1 is equal to 1, which is definitely less than 3. All right. And we also, since the a1 is 1 and it's an increasing sequence, so this sequence is always positive. So we can see that. And 2. All right. Why don't we assume induction hypothesis? All right. When n equals k, all right, AK. Oh, we have to assume. So we assume that AK is bounded above by 3, right? And also AK is a positive quantity, right? Then what we want to do is number 3, induction step, right? When n equals k plus 1, right? We want to show that AK plus 1 is less than 3. Right? So let's start with AK plus 1. Right, by definition, this is 3 minus 1 over AK. Right? But since AK is a positive quantity, you are subtracting a positive quantity. So definitely this is going to be smaller than 3 because you're subtracting a positive quantity from 3. So it's going to be less than 3, right? And that verifies it. So therefore, we know that, so hence, we can say hence, for all n, which is natural number, an is bounded above, I should say n is bounded above by 3, right? So this will verify that an is bounded above and by 3, right? So this is part A, right? So let's look at the part B, right? Actually, they don't call it part B, but we want to determine whether the sequence converges or diverges. If it converges, find the limit, all right? So let's do that part. All right, so we show that it's increasing, so it's monotonic, and bounded above and below because it's all positive. So therefore, by the theorem, we know that the limit exists, right? So we know that the limit exists, and then we have to find a limit, right? So let's find a limit. So what you need to do is look at this recursive formula and take the limit of both sides, right? So limit of an plus 1 as n approaches infinity is equal to 3 minus 1, or actually we have to take the limit. So limit, right, we take the limit of the right hand side, which is 3 minus 1 over an. Right? Since we just know that because of the theorem, an limit exists, so when you take the limit of this guy, this is going to have a limit, so let's call it L. And the same thing, if you take the limit of an as n approaches infinity, so this is going to be L. So if you have a limit, then it has to satisfy the following equation. So this is going to give us, right, L is equal to, right, 3 minus 1 over L. Right? Then we can just solve this equation for L. So multiply both sides by L. You have L squared is equal to 3L minus 1. Right? Then we can put everyone on one side. So I'm going to subtract 3L and add 1. So we get the L squared minus 3L plus 1 is equal to 0. Right? Then we can use the quadratic formula to find L. So L is going to be equal to, right, negative b, so it's 3, plus or minus square root of b squared, which is 9, minus 4 times a is 1, c is 1, so minus 4, and over 2 times a, so 2 times 1, so it's 2. So we have 3 plus or minus square root of 5 over 2. Right? Then we have two choices. And if you look at the 3 plus square root of 5 over 2, and then we have 3 minus square root of 5 over 2. Right? And we know that this sequence is increasing, so it's start from 1 and bounded above by 3. So it can't be both numbers. So which one is the right one? So when you do 3 minus square root of 5, so square root of 5 is bigger than 2. So 3 minus something bigger than 2 over 2 is going to be actually less than 1. So we know that it's going to be the positive 1 is the answer. So therefore, the limit L is going to be equal to 3 plus square root of 5 over 2. Right? So let's type it in. We get 3 plus square root of 5 and all over 2. Right? So let's check the answer. Submit for testing. Alright, looks like we got this one correctly. Alright, that's it. I hope that this was clear.